We're going to start recording today with these beautiful visualizations of what the atomic orbitals look like for hydrogen. And I know that what you're looking at right now might not make a whole lot of impression yet, but that's okay. I'm going to talk you through some of it, and we're also just going to kind of enjoy how people have visualized some of this stuff. The real reason that I wanted to talk about these orbitals some more was that we need to understand the nodes a little bit better. So what am I talking about in terms of nodes? You can actually see them really well in this image, and that's why I'm starting you out here. These nodes are the dark places in between the bright places, right? So we had two kinds of nodes. We have radial nodes, and those look like a ring or a sphere. And we have angular nodes that look like just a dividing line, so maybe like a plane if we were in 3 dimensions, or just a line. So take a moment here and look at this beautiful picture and try to identify for yourself some of the nodes that are here. Let's start with looking at some of the angular nodes. Remember, the angular nodes are the ones that look like planes. There aren't any up here, but there's one right here. There's one right here. There's one through the middle this way. We have one going through here and one going through here. One in between here that we can see. One diagonally and this way diagonally. One right here. We could keep going. But let's look at a few radial nodes now. So we've got one right here, a little ring. This one appears to have 2. We've got a little ring right here in the middle, and another one here. None on this line, but this one has 1, 2, 3. This one has 1, 2. All right, so we could keep going here too, but let's go ahead and put down what we've seen so far. So with our nodes, we have 2 types of nodes that we've discussed before, and these are angular and radial. And when we look at an orbital, the total number of nodes for any orbital is equal to n minus 1 for that orbital. So if you have an orbital that has n equals 5, any kind of orbital in the n equals 5 shell, then you will have n minus 1 would be 4 total nodes. And of those nodes, we can have 2 different kinds. The number of angular nodes is equal to the angular momentum quantum number, whatever that number is. And the number of radial nodes is just the difference between the 2. And we write that as n minus L minus 1. So let's look at the orbitals that we've seen so far and match them up with the nodes that they have. So we had a 1s orbital, which looks like a little sphere. At least that's how we drew it. And we know that this is the n value and this is the L value. So we can figure this out. N is equal to 1, L is equal to 0 for S. So when we check on our total number of nodes, we have n minus 1. 1 minus 1 is equal to 0. No nodes on a 1s orbital. And that's just what we expect, right? We didn't actually see any there. So let's look at 2s. In our little cutaway of the 2s orbital, so we kind of drew it like that, right? We could see that there was a middle portion, and then there was a little node, and then there was another middle portion. Okay, So n is equal to 2, but L is still equal to 0. So our number of nodes, 2 minus 1, is equal to 1. So we have one total node. L is equal to 0, so that means we have no angular nodes. And so that must mean that this is a radial node. And that makes sense, right? The radial nodes look like a little ring, and that's exactly what we have right here. We also looked at a 3s orbital, and it looked very similar to what we saw right above here. We had two rings in our little cutaway. N is equal to 3 for the 3s orbital, but L is still equal to 0. So let's take a look. Since L is equal to 0, we concluded that there were no angular nodes, and that's still going to be true. It's true for all of them. There are no angular nodes in the 1s orbitals, or excuse me, in any of the s orbitals. So that means that our number of nodes is now 3 minus 1, or 2, and these must be radial nodes. And that's exactly right. This is one radial node, and this is one radial node. So it's just what we expect. Let's see, for 2p orbitals, we have an orbital that looks something like this. N is equal to 2, L is equal to 1. We have our number of angular nodes is equal to L. So we definitely have one angular node. But N is equal to 2 again. And so our total number of nodes for N is equal to 2 is only one node. And so that means that this 2p just has one angular node. And that's just right. That is right here. That's this plane that would be right here. In 3 dimensions, this plane would be sort of in between these orbitals, if that makes kind of sense there. Okay, we also looked at a 3D orbital. Most of these 3D orbitals looked kind of like this. Oof, that's not a very pretty one tonight. Sorry about that. So N is equal to 3, and L is equal to 2. So we have two angular nodes. And we just had N is equal to 3, giving us 2 total nodes. And so that must mean that these are our 2 total nodes. And they're going to be right here in between my lobes. And those are those 2 nodes. And they also would be planes just like up here on the 2p orbital. So let's switch back really quick and take a look at some of those orbitals that we just were looking at. So look, what we have here on this website image is the quantum numbers n, l, and m sub l. So if we have n is equal to 2 and l is equal to 0, this is, you recognize it? This is our 2s orbital. And you see this one? This is our 3s orbital. Can you find the 4s orbital? Right down here, right? So these two are both 2p orbitals. You can see their planes in between, their planar nodes, angular nodes here. Sometimes I call them planar nodes. And here's a 3D orbital. Here's a different 3D orbital. So we've got lots of different orbital representations. So you can actually use what we know so far about nodes to predict what some of those other orbitals look like, and some of them you saw on that previous image. So let's take a minute here and actually look at what was different first between our 1s and our 2s and our 3s orbitals. So take a look here and see what's different. It's the number of radial nodes, right? And it's because our n is increasing. So we went from 0 radial nodes and 0 angular nodes to 1 radial node, still 0 angular nodes, to 2 radial nodes. And these have no angular nodes because L is equal to 0. Any s orbital that we have is not going to have any angular nodes. So let's take a look at what we would think would change if we go from this 2p orbital to a 3p orbital. Is the angular node going to change? No, because we still have the same p value, right? I mean, the same L value. These are both p orbitals, and so L is going to be 1. We're always going to have one angular node for a p orbital. But if we go to 3p, that means our n value increases, so we also would have a radial node. And the way I usually draw orbitals that are larger, like when I go from a 2p to a 3p, I always just start with the 2p orbital. And then I draw my radial node around it. And I also draw my angular node. And then I draw 2 more lobes of the orbital. And I make sure to shade. They'll always be opposite. So if this is non and this is shaded and this is not shaded and this is then this is going to be shaded. We always change. This is called phase. So these two have 2 different phases. And we're always going to change phase across a node. And what that really is coming from that mathematical function where we would probably have something like this in our mathematical function for this thing. Okay? So we know that these little places where we cross the axis, these are the nodes in a mathematical function. They're the zeros. And we also have in our mathematical function, this part of the function is positive, and this is negative, and this is positive. So we can say these are the parts that are changing phase. And that's what we're trying to represent when we draw this. Okay? So any p orbital that you draw, I don't even care what it is. You could draw an 18p orbital. I'm not going to because it would take up a lot of space. But we can think about it, right? What kind of nodes would it have? We would have a total number of nodes. Maybe 18 is kind of a little silly. Let's just do 8. Total number of nodes is n minus 1. So that's 8 minus 1 is 7 total nodes. L is equal to 1 still. So we have 1 angular node. And then the other 6 are going to be radial nodes. So what would that look like? It would look like something like this, only instead of just one of these spherical shells, we would have 6 of them, and each would be larger than the next, and that's why I said it would take up a lot of space, and so I'm not going to draw it. But you can draw any large orbital this way. So why don't you challenge yourself and see if you can draw a 4D orbital here. So do like what we just did. Look at your total number of nodes and your L, and then how many are left. Pause the video and give that a try. Okay, hopefully you found that we have 3 total nodes, and 2 of them would be angular, and then 1 must be radial. So we would draw this by starting with our 3D orbital. And here's my nodes for that one. And then I draw Those are my two angular nodes. I'm going to draw my radial node around this, and then I'm going to put my lobes, kind of like, I don't know, little hubcaps or something, or bananas. This one needs to be shaded. And then we'd be done. Okay? So this is the same pattern regardless. You just draw the basic orbital, whichever kind it is, and then add some radial nodes, and then you're done. So one last thing on this diagram before we're done here. So look at these numbers. This is the N, L, and M sub L numbers for each of these orbitals that are listed. So it's easy to identify the N number. It's a little bit harder to take the L and convert it into our S, P, D, F, etc. So remember, S is 0, P is 1, that's going to be the middle number, D is 2, L equals 2. So we've got several different D orbitals. And then we also have F orbitals. So these ones will be our F orbitals. Okay? They have L is equal to 3. I'm mostly not going to ask you to draw these F orbitals though, so you don't really need to worry about it. But I do want you to be familiar with the shapes of our basic atomic orbitals and to be able to draw at least the next couple of orbitals based on the number of nodes, just the way we just did.